Hello everyone. My name is Minji Chen. I'm a faculty member at the Princeton University. Today it's my pleasure to host the number 6 tutorial of MagNet Challenge 2. We have quite a lot of tutorial this year because we're facing a more interesting challenge. First of all, I want to mention this. We lost Haoran about 1 month ago, and it was heartbroken. We received many condolence emails from the community. Thanks everyone for checking in. We're doing okay. We are recovering. Hyukjae and Hyukjae experienced extremely difficult time, but they were still able to pull everything together. Thanks everyone for your support. I believe Magnet Challenge is also in Haran's heart. He wants us to do it well. So we'll continue to make sure we complete manage Magnet Challenge 2 and hopefully lay a foundation for the future. Just a few quick announcements. Today we're having tutorial 6, and we'll be talking about the rules and the data and the structure of the data for the final evaluation. About 2 weeks from now, mid-November, we'll release the final testing data, and you have 2 months to finish the test and submit a report. At the same time, it's also optional. If you have a model that you think it's interesting, feel free to submit a pre-testing report. Just help us to get a sense of how deep you are. So we hope to get a feeling how many teams are still actively participating, so that we can prepare for the final evaluation. We know how many final results, because if you have a functioning model now, then most likely we trust you'll be able to submit the final report. So that's the whole purpose of it. But again, it's optional, and it doesn't have any influence on the final evaluation. You can just show up in the final evaluation. You don't submit anything now. The other thing is, after January 15, when you submit your final result, we will be evaluating the result only. And if your team are winning or think has a very high chance of being awarded, we will be asking for codes so that at least we don't need the training process. We don't need to know how do you find your model. We only need to know how does your model look like, and we can execute it or run a model so that we can verify your results. The other thing we are looking for is a full-page write-up, maybe 2 weeks after you submit the final report. It doesn't have to be polished, doesn't have to be perfect English, but somewhat documenting your ideas and concepts, because eventually, as a part of our final evaluation process, we'll host a meeting, and all the winning teams will be invited to give a presentation about the ideas that you're proud of. Like, what do you think differentiate your model, and what do you learn during the process? What has worked and what doesn't work? So we're happy to hear all of those results. So in general, we think it'd be helpful if you try to put together like a full-page simple write-up with non-perfect English, but documenting your general idea. That will be very helpful, and will be helping us to process the results and select the winners. So these are some of the house cleaning announcements. Feel free to raise your hand if you have any question during the presentation, and we'll be happy to run this tutorial or today's meeting as in a more casual, relaxed way. And we hope to hear your feedback so far, because I believe everyone, if you are here, you must be participating in the challenge. You have some feedbacks, and you have something that you want to let us know. Then Hyukjae, please go ahead.
Yeah, thank you. Hello everyone, and welcome to the MagNet Challenge 2 Tutorial 6. My name is Hyukjae Kwon, and I'm very happy to guide you through today's session. Over the past few months, we've gone through several tutorial sessions, exploring data structures, neural network methods, analytical methods, and evaluation procedures. Today, we've reached out one of the most critical milestones in this challenge, the evaluation datasets tutorial. The main goal for today is clear. I'll explain how the final evaluation dataset is structured, what's included in both the training and testing data, and how you should prepare your models for prediction and submission. By the end of this session, you will have a complete understanding of the dataset files, what they contain, how they relate to your model inputs and outputs, and how to use them properly for the MagNet challenge. Now let's take a closer look at the binary evaluation dataset. In this stage, we will provide the 5 new materials labeled simply as A to E. The material names are kept anonymous to ensure a fair evaluation. We don't reveal the real material type so that all participants are judged only by their model's performance, not by prior material knowledge. So if you go into the evaluation dataset, you will see 2 folders named testing and training, and each folder contains the 5 folders named material A to E. And if the training data includes the 3 types of CSV files, which are the B, the magnetic flux density sequences measured in Tesla, and H, the magnetic field strength sequences in ampere per meter. And also T, the temperature profiles corresponding to those magnetic measurements. So you can see those 3 types of CSV files in training and also in material A folder. The testing data also includes 3 CSV files, but their meaning is slightly different. B provides the input B sequences for which you must predict H. H padded provides the past H segments, allowing your model to use historical information. And again, T gives the temperature during each sequences. In other words, during testing, you will receive the partial input sequences, a few H values, a B waveform, and also the temperature. Your model must then predict the corresponding H responses for the new segments. This setup is designed to simulate the real-world transient prediction where only limited historical information is available. So in testing data and also in material A folder, you can see those 3 CSV files, the padded H sequence, B sequence, and temperature. So these are the evaluation data format for testing your models, similar to the pre-evaluation data set we introduced earlier. All measurements were sampled at 16 MHz, which means a time resolution of 62.5 nanoseconds. Each material was tested under 7 excitation frequencies from 50 to 800 kHz, covering a wide operation range from low to very high frequency. We also introduced the 3 temperature levels, the 25, 50, and 70 degrees Celsius, to account for temperature-dependent material behavior. And as you can also see, each test dataset contains 1,000 time steps of B and H, divided into segments for prediction tasks. These segments include different known to unknown ratios. In other words, the input and output ratios, which are 10 to 90, 50 to 50, and 90 to 10, measuring your model, meaning your model must predict varying length of future H responses using different amount of past H information. Overall, there are about 1,000 testing segments per material, providing diverse conditions across frequency, temperature, and prediction horizon for your model to handle. Now let's talk about the evaluation data submission. The objective is simple. For each HT sequence, your model should fill in the unknown portion using its prediction. There are a few important submission rules to keep in mind. The first one is the order of your predictions must match the provided sequence exactly. Any reordering can lead to mismatching in scoring. And also, you must submit the entire HT sequence, including both the known part, which is providing the datasets, and also the unknown part, which is your predictions. For example, if a sequence contains 100 known steps, and 900 unknown steps, your submission should include all 1,000 steps, with the first 100 matching the dataset and the remaining 900 filled by your model. Following these rules ensures fair and consistent evaluation across all participants and avoids accidental errors during scoring. So you will then submit those 5 CSV files from each material A to E. So let me give you a concrete example of how to submit your predictions. You will see a file named material H padded material A padded H sequence, the CSV file, where the unknown H values are marked as non-values. Your task is to fill all known values using your model's prediction for every data point in the file. Once you've filled in the predictions, save the complete H sequence using the following format: the H material name, the CSV file. This ensures that the submission is correctly formatted for automated scoring. Remember, do not change the order of the sequence and include both the known part and the unknown part of the prediction values. Now let's go over the evaluation criteria, which are the same as in the pre-evaluation phase. It will show how your model predictions will be scored. There are 2 main metrics we use. The first one is sequence relative error. This metric measures how well your predicted H sequence fits the characteristic response of the input data. Mathematically, it's expressed as this equation. And in simple terms, it's the root mean square error of your prediction normalized by the actual measure sequence expressed as a percentage. The second metric is the normalized energy relative error. This metric looks at the magnetic energy or core loss in your predicted segment compared to the total core loss of the full sequence. It's calculated as this. Here, the T0 and T3 are the test start and the end of the full sequence, while T1 and T2 define the start and the end of test segments. In essence, this tells us how accurately your model predicts the core loss in the test segment related to the total loss of the entire sequence. Together, these 2 metrics evaluate both sequence match accuracy and core loss accuracy of your model predictions. Now let's talk about the data that will be provided for the evaluation phase. For each material, the number of sequences is summarized in the table on the slide. The important thing is the training and testing sequences are selected differently for each material, so your model must handle diverse conditions. For example, the material A is a tiny data challenge with only a few training sequences. As you can see, only the 105 sequences are provided for the training, and rest are for testing. Material B is a frequency challenge where some frequency sequences are used for training and others are reserved for testing. Material C is the no past H data challenge, which I'll explain in detail on the next slide. Material D is the flux density challenge, which is similar to material B. Certain flux density levels are used for training and others for testing. And material E is the special materials challenge, which has a unique characteristic compared to the other materials. The training and testing sequences will be released on November 15th, and the complete dataset will only be made available after the challenge is completed, at which point it will be open sourced.
So just to add one more thing, all the material, the training sides is basically we carefully tailor different training data for you. And then we randomly select about 1,000 out of the entire data set for testing. So that's sort of, we create different type of challenge for you by customizing different training data for different material, which may be true in a real application scenario. But we suspect you don't have to change the way you train. your model. Hopefully your training process will automatically adapt, or you can apply advanced technique like transfer learning or so, but it's not mandatory. It's all your own choice. How do you want to handle different challenge? You can use different training process for different material, or you can use the same training process for different material. And we look for novel solutions to address these kind of challenges.
Yeah, thank you. So now let's move on to the material C, which is the no path H data challenge. Here, unlike the other materials, only the initial value of H is provided, which is 0 ampere per meter. In other words, your model will not have access to any previous H sequence data for this material. This setup tests your model's ability to predict H purely from the B sequence and temperature without relying on past H history. I think it's an important challenge because in real-world scenarios, you may not always have historical measurement available, so your model must be able to generalize from initial conditions and inputs.
Right. So this is a test which could be very interesting because in reality, MagNet material has memory, but not in all cases you remember all the memories or have measurement to capture all the memory. A good model, we're just hypothetically, we don't know how to do it, honestly. We'll after you run a system for long enough time, you reach some kind of steady state. So regardless of where you start, your system will always reach some kind of states. And we are hoping, well, this data we use for testing is started from zero. It's sort of like cold start. We demagnetizing material, make sure everything is go back to zero, and we start. It's basically we're asking you to predict the step response of a material against a particular excitation B, which could be a real scenario where you are building like power converters, like working pulses or so. So that's the purpose of this test, which is a little bit different from other tests where we run the system in steady state and we ask you to start to predict sort of in a quasi steady state. This is more like a cold start scenario. You can assume all the edge before this is zero, and that's actually what we measured. We basically make sure the edge is sort of zero starting from in the past. Hyukjae, we probably should make it clear in the document, like the teams can assume the edge before zero is also zero, right?
All right, okay, I'll mention that.
Yeah. You can add a text in this on this slide.
Okay, yeah, I see.
It's more of a zero start. It's like we know the past in the past is zero. Yeah.
Mhm.
Yeah.
All right, then let's go over the visual submission process. First, rename the main folder with your team's name. For example, the name of your university or lab. Next, place all your output CSV files inside the subfolder named the result. You also have to include the parameter size CSV file where you clearly indicate the number of parameters in your model for each material from A to E, like this table. Then compress the entire folder into a zip file for submission by January 15th. Also, prepare a 4-page final report in PDF format by January 31st.
TJ, I remember in Magnet Challenge 1, we provide a script for the teams to run to check how many parameters they have. Do we still have that script available?
Yeah, in the testing code, we have the count parameter function. So yeah,
Okay.
they can use it.
Okay, yes, just make it clear here. So because there are teams which are probably just new to Magnet Challenge 2, we can let them know there's a script you can call to quickly find the number of parameters on your model.
Yeah, I'll also add that here.
Okay, thanks.
Yeah, so to wrap up, let's review the key steps and dates for the Maya Chance 2. The first, the training phase. On November 15th, the final evaluation data will be released. So you can download the training and testing datasets for the 5 additional materials A to E from either MagNet Challenge GitHub or MagNet X GitHub here. And use this data to train, tune, and refine your model or algorithms. Then predict the future H sequences for the provided segments, filling all non-values in material padded H sequence CSV files. The second step is the final model submission. Until January 15th, submit your final model predictions. This includes the 5 separate CSV files, one for each material, along with the number of parameters for each material. All files should be submitted to the pulsemagnet at gmail.com. And finally, on January 31st, submit a 4-page report in IEEE TPL PDF format, briefly describing your key methods and concepts. In February, we will ask some teams who are in the ranking to submit their trained models and also the codes for evaluation and final ranking. Following these steps ensures that your work is properly evaluated and that your model's performance is fairly ranked in this challenge. Yeah, so that brings us to the end of today's tutorial on the MagNet Challenge 2 evaluation datasets. Thank you all for your attention and participation today, and we encourage you to start exploring the evaluation dataset as soon as they are released. Refine your models and submit your predictions on time. Now, now if you have any questions, I'd be happy to answer them.
Great. Thank you, Hyukjae. So we do have two questions here. One is, can you please clarify if the final model should be a material agnostic? The answer is no. You don't. You can fine tune every model for every material because fundamentally, it's not sure. I'm not sure. We are not sure if all the material should be used trained and evaluated with one model, or each material should be customized for following a different approach. So we're looking for a method. So we will be happy to see if you justify that you find a commonly used process to find a useful model, good enough model for all material, and they all end up look similar or the same. Or you have an argument saying by looking at the data, you decided to use different method for different material, and all of them will be evaluated together. So in the end, we are going to, for every team, will have an accuracy, 95 percentile accuracy for both RMS error of the time sequences and the core loss error. And then we'll create a table. And for the table, each table will be 5 materials. Then how does this team do for each of the challenge? And the judging committee will decide based on all of this. So we'll find an angle to differentiating your method and evaluate the value, and we see the potential contribution from many aspects. And that's the beauty of MagNet challenges. In the end, it's an open-ended challenge. Second question, maybe Sai, I can allow you to talk. So second, also, can you please let us know if we need to maintain the window size as 1000? I think as Hyukjae mentioned, we hope you just fill up the CSV file. The CSV file for every sequence is 1000. Some of them we provided 200 and ask you for 800. Some of them we provided 500, ask you for 500. So we hope you just submit a completed CSV file with every sequence of 1000 step. And that's what we do for this challenge. We just choose 1000 because we feel it's long enough. It's not too short, and it's also long enough. 3, are the 5 materials part of the material that are provided previously? And the answer is no. There are 5 new material. It doesn't exist. It's not included in the 10 material that we have already provided. There are 5 new materials, but they are very similar. At least 4 of them are very similar to the 10 materials there. You may find, oh, this material may look very similar, and that may be true. And there's one material which we think is interesting. It has interesting behavior, and we call it new material challenge. And we provide enough data, and in the new material, that new material challenge, we think we provided enough data for you to just train the model from scratch. So there's some echo going on. Sai, are you speaking? I think his mic has some issue. anyway. So then I'll make you Liu Chen. Yeah, will the frequency information be disclosed for the testing data? Do we need to identify the switching frequency using FFT or some simple method? It's your choice. No, we are not going to release the frequency or the switching frequency of the power stage while we are testing the material for the new data. No, you can do whatever you want. You can try to detect it if your algorithm needs it, or you don't have to use it. Because the ultimate goal for this year's challenge is for arbitrary waveform, and arbitrary waveform may not have a frequency pattern. So it's your own choice. Although we know that the way we are testing this type of data, we do have some frequency pattern. So if you need that frequency pattern, feel free to use whatever algorithm you want to use. And the data is sampled at 16 megahertz fixed. So you can reversely identify what are the effective frequency we're running. The next question is, in a 1,000 steps for each BE, how many subcycles are present? Are the number of subcycles the same across all sequences and materials? The answer is no, because we're sampling at a fixed frequency. So for different effective switching frequency, you'll get different subcycles. And you can look into the data. So they are different. You can reversely calculate. Once you identify the switching frequency, you can figure out how many subcycles we have. But no, so for different material in different testing, so think about the excitation as we are trying our best to make it arbitrary. Although, as we mentioned, it's a quasi-static. It's not real arbitrary. For most of the challenge, most of the data is sort of in a quasi-static steady state. So we know where the edge and where the B starts. Um, Final one. Not final one, the last one. Can you clarify whether or not if we need to submit report result on the 15th of November? And the answer is no. You're not mandatory to submit your preliminary testing results on November 15th, but you're encouraged. It'll be helping us because we really need to know how many teams are still participating. We don't want to like lose our hope. Nobody submit the preliminary results, but then 20 teams show up in the final round. So if you are confident you have something that you're happy to show, uh, you are encouraged to submit something to us so that we got some positive feedback because we are really look forward to like our team. We have been running open loop for a few months. Some feedback will be extremely encouraging for us to see the results from you guys, but it's not mandatory. Uh, Next question. So regarding the parameter numbers of extraction, will the code be compatible to MATLAB? What does that mean? Uh, Regarding the parameter numbers extraction. Oh, so MATLAB, I see. So if you train your model with MATLAB, how do you report your number of parameters? I think MATLAB, if I remember right, MATLAB also has a way to find the number of parameters. Maybe Hyukjae and Shukai, you guys can look into that a little bit. And we also provide a way for the teams to report their number of parameters in MATLAB.
Yeah, sure. I'll look into it.
I think Mian Liao is quite familiar with training neural network models in MATLAB. You can talk to him. Maybe it's just one function. Most likely, it's just one function we need to call, and we'll report how many parameters we need.
Sure.
Yes. And then Sai. Hi, Sai. You are
Hello,
muted.
can you hear me? Yeah,
Yes, I
can
can
you
hear
hear
you
me?
now. Yes.
Yeah. So what I'm asking is like why I have asked about material agnostic is, so if the five materials are are a subset of the 10 materials that has been provided, okay, then these five materials prediction should be on a single model, or these five material, if it is not material agnostic, and if we are giving you 10 different models for the 10 different materials, then each of the five materials should be tested on each model, or how it has to be done.
So for the five new material, it's new. They're not the 10 material. It's just new material. Nobody
Okay,
has any
okay,
information. Yes, new.
Okay, okay,
And you
okay.
decide what do you want to do. You want to train a new model for each material, go ahead.
Hmm, hmm.
Or you want to say, I find a general way which can cover a lot of material, which is also very valuable. So we leave it open to you.
And one more doubt I have, this is related maybe from the practical point of view I'm asking. Now let us consider that I have a power converter, okay, where I am keeping the duty ratio and the switching frequency as constant, but I am changing the load on my, I am changing the load in such a way that the load current is changing, okay, but my voltage is constant. If that is the case, then how we can use the developed AI model for that
That's DC.
use case?
If it is
Yeah,
a buck converter, it's a DC bias, right? So
yeah,
if
yeah, yeah.
load is changing, you're basically changing the bias. And that's why this transient model, a good transient model should also work in steady state. That's what we already described. Every time you feel free to use the data provided in MagNet Challenge 1 to test your model. So every good a good transient model should work well for steady state as well. So what you're saying is that if a steady state, there's a steady state DC bias change, and we
Yes.
hope, we don't know how to do it. Even us, we're not confident our own model, because mo most of our time was spending on organizing the challenge. So we don't have the best model in hand. So I would say maybe one of you guys can find a good model which will continuously give you good results. If your edge, basically your edge start from different point, right? Your edge may start from zero. That's when your converter start from 0 amp, or your model work well when edge has a particular starting point and you get just maintain it, run it continuously over there. So we don't know. We leave it open to you, but we trust a good transient model should cover the case you just described.
And can you please repeat on the materially testing? Uh,
What do you mean by that? The material we are testing?
uh, Material
Oh,
E
material
for
E.
thingy.
So
Yeah.
the material E is we did a quick examination of material E and we find some interesting behavior in the patterns, like how does the core loss change with different factors. And we that's why we leave it as a special material challenge. We provided 6,000. You can see it's quite a lot of training data. We provide 6,000 sequences, and we're asking you to predict 1,000 out of it. But these
And
six,
flux
1,000,
density. Yeah.
yeah, go ahead. Yeah, yeah.
Yeah. And flux density challenge meaning?
Density challenge means that we give you there's some gap in the flux density that we don't give you. Like we give you some low flux density data and high flux density data, and in the medium range you don't have any data. And we hope your model somehow can either learn from other materials or you have some interesting pattern building so that it can try its best to predict the region operating range that there's just no data available over there. But the material is normal material. It's not a strange material. It's a material which looks like other materials.
Thank you. I have no questions.
Yep. Great. So don't be scared. I guess if a challenge is challenging for you, it may be challenging for everyone. So we expect you, like for example, special material challenge or tiny data challenge, the accuracy could be low, but it is what it is. Like in the real world, there are challenging problems too. So next question, I believe is welcome. Do normalization constants count as model parameters? The answer should be if the normalization constant is uniform across different material, they don't, because that's counting as your algorithm. But if you have to change your normalization constant for different material, then it should be counted. So basically what we are looking for is material specific parameter. So what numbers you have to change for different material, or how much memory in your model you have to remember for modeling this particular material. So some of this could be controversial. So do your best judgment, and I believe won't be missed too much. I like if you have, yeah, we can discuss about it case by case. scenario, but in your report, try to do your best so that that sort of makes sense in your mind. Our philosophy is we're evaluating how much memory, how much specific material character, just like a physics model, how many parameters you need the model to remember for each material. We are evaluating a model size in a similar way. How many material specific parameters your model need to know, regardless if it is a normalization constant or if it's a weight in a neural network. Uh, does this answer your question, Wilhelm? Let me enable. Welcome. Does that make sense? We
Yeah,
can.
that makes sense. Thank you very much.
Yeah, I know there could be gray zones, so just try your best. Uh, the next is anonymous attendee. If the model use n parameters for material A and two parameters for material B, what number should be reported for the number of parameters? So report both. So you can create a table with accuracies and number of parameters for each material. In the end, it's just five. We can look at it. And we will appreciate both. If you use a uniform modeling architecture for all different material, great. Or you have a clear and good reasons to apply different modeling strategy for different material. And keep in mind, in the end, we have outstanding performance award and outstanding novelty award. So performance will be just judged by performance, but the novelty can come from many different ways. Can come from the way you quickly evaluate data and decide which modeling strategy you choose, or can come from well, how do you find a general approach to model many different materials? Next question, Liu Chen. We prefer to build a separate code to identify the frequency information based on the provided B sequences. Can you please explain the frequency challenge again? Are there missing value for certain frequencies that we need to predict? Yes, that's the same as the amplitude challenge. So we'll provide you some data for low frequency excitation, some data for high frequency excitation, and you'll find there are some gaps in the middle where we're looking for you to tell us how does it look like. And that's the other way we try to make sure your algorithm is really tailored towards like true arbitrary wave. So maybe the frequency is just changing. So that, yeah, we can tell you in this challenge we don't. For every sequences, we are continuously exciting with a fixed frequency, but the duty ratio can change dramatically, and the bias can be changing dramatically. So from large signal perspective, it's more or less like an arbitrary wave. But yes, you can still try to detect the frequency. Just like in a real arbitrary wave, you can have a moving window, and a moving window detect the frequency, and you still use frequency as the data. No one stops you from doing that. It's your own choice. Uh, I hope you answered the question. I answered the question. And next, could you please explain the frequency challenge again? Oh, okay. I've already mentioned. Yes. Yes. So there will be gaps in the frequency for the training data. And then we ask you to tell us the results for the testing. Final last question. Hello. Thanks for organizing the meeting and challenge. A basic question. Is this competition more related to the power electronics model or deep learning models? I don't understand the question. What does this mean? Do you want to tell me who you are and I can allow you to speak? The last question come from anonymous attendee. What does this mean? I think they're both. We are both asking for, we're basically creating a scenario which is very specific to power electronics. Although other areas may have similar, but it's particularly tailored for power. Deep learning model, we are interested, but we don't ask for, if you have true novelty in developing new deep learning model, that's great. But in the end, you will be evaluated by first the performance, which is just ground truth, uh, and second the novelty, and the novelty should be related to power electronics domain knowledge, and that's where we're not just trying 100 different models and then select the best one, and without knowing why. We hope you'll be able to tell us a little bit why you think a particular modeling strategy makes most sense, uh, and show us the result. So I would say we are attacking this challenge from power electronics perspective. You are encouraged to be innovative in every aspect, but try to make sense of your innovation. Just don't with just trial and error, or you show us the best model without telling us why. You can still win the best performance award. But for you to go for the best novelty award, we hope to hear why.
I'd like to add about this question. I think so. The goal of this challenge was more or less where the data we provide are heavily towards power electronics. The data we're collecting are very power electronic, but um, but again, I think you can develop data-driven methods. You can develop deep learning models, but also you can develop physical models, or a hybrid of both. So I believe this is more or less really a material modeling problem where we're trying to use this challenge more or less trying to see if your model can explain the material's intrinsic behaviors. And so that is more or less what the goal is. So yes, what we provided previously with the machine learning models are a specific example of it. You are more than welcome to use the data we provided to develop other physical models or any other analytical models. It's not a pure, let's say this competition isn't revolving around deep learning models. It's about how you can develop a model using any technique to describe the physics of the material, the physical behavior. And so that's more or less what this challenge is about. But yes, you are more than welcome to use deep learning models.
Right. So yes, I guess we're not geared towards deep learning at all. And fundamentally, actually, my personal intuition is this problem probably is not a deep learning problem. Like we're just trying to predict the next effective differential permeability of the materials that you know where the next steps are. It shouldn't be that deep, but who knows? We wait for you to tell us how deep it should be.
Hi, can you hear
Hello?
me?
Yes?
Hi. My question is still regarding the frequency information from the testing data. Do we need to put the function in our model code, or we can identify the frequency information using a separate code?
That's indifferent for us. It's it's okay either way. Shukai, right?
Yeah, so
As the reason why I ask this question is when we try to extract the frequency information, we prefer to use the full length of B, not the feeding partially length of the B.
Understand.
Yeah.
right.
So go ahead, Shukai.
Sure. I only have one, I guess one sentence answer for this is, whatever you do, it doesn't matter, but think of if the data we provided does not have any frequency information at all, meaning if my excitation to the material is purely arbitrary, there's no such information as frequency. It's completely random. The strategy you use, will that still work? So the goal of this, right, is more or less without thinking about using frequency as an extra input, right, is your model able to depict any arbitrary excitation at all? Obviously, using frequency is great, but that's more or less sort of we're restrained by the data itself, right? The data we created
yeah.
have frequencies, but
Yes,
if it's like a stock market prediction, then can your model sort of predict without having any input of frequency?
okay, but for the current data we have, all of them are fixed
Yeah.
switching frequency, right?
Yeah.
Correct.
If you
Yeah.
if the testing data are variable switching frequency, then I think it makes sense for the model we can do arbitrary switching frequency.
Right.
So
So I think my answer will be this.
mhm,
For submitting the CSV, do whatever you want. But if
mhm,
you are selected as winners, we have to replicate your method. Make sure if you use two separate code, make sure we can do it too,
mhm,
on our side. And then third, if you're aiming for performance, it doesn't matter. But if
mhm,
you're aiming for novelty, the judge
mhm,
committee may say, "Oh, your algorithm needs this frequency information so that it's less applicable for a real arbitrary wave case." So that would be
mhm.
my answer to your question. Like it's your choice whether you want to do it or not.
Okay, sure.
Yeah, you
Thanks
can
a lot.
always infer the frequency and you don't trust it, or you just your weight, the weight you put on the frequency you get is very low, and I don't see any
Mhm,
problem with that. I think
mhm.
that's still a valid method.
Okay, thanks a lot.
Yeah, great. Um, okay, there are more questions. When referring to performance, do you plan to factor in the model size as well? Suppose model 1 with 1700 parameters shows 6% error, and model 2 with 1800 parameters show 5.8% error. Would you consider model 2 to be better than model 1? I think that this is a tricky question and we receive it all the time. In the end, what we'll do is we'll do something like MagNet Challenge 1. We'll plot an X and Y graph with X accuracy on one and then Y on the other. And we'll plot both absolute accuracy, absolute number of parameters, as well as the ranking of accuracy and the ranking of the model size. And then we'll present it to the judge committee and let them decide. We hope that in the end we can find a fair, transparent criteria because everything will be transparent, open source in the end. So we hope we will try to find an angle so that we can differentiate why we think either we select both as co-winners or we can show you a reason why we think one model is slightly better than the other. So we hope with these the tricky part of this evaluation is there's no absolute winner, but on the other hand, we hope that they are after we look into the reasoning and the philosophy behind your method, we will be able to tell, or maybe the other team win in performance, but you win on novelty. It could be a scenario in those cases as well. So don't worry too much about the absolute ranking up and down. You will ultimately the good result will follow you if you have good models. So that will be my argument, and we'll be able to find more money. If we find too many winners and too many models, that's a really good trouble to have, and it's easy to find money to give more awards and prizes. And last one, can you please give some inputs related to handling higher window size? Not sure. What do you mean? Sai, do you
I
want to come?
think I think the higher window size means I'm assuming you mean the memory window, not the test window, right? You mean the given, let's say 1,000, we're asking, okay, we provide 100 data points, asking you to provide 900, and you use your model to predict 900. What is the window size you're supposed to use for the model? That window size is determined by you. The higher the window size, obviously more compute resources you will require. And obviously, if we were only providing 100 data points and your model requires more than 100 data points, then you will have to populate, right, the most distant gaps with whatever number you wish to populate it with. So your model should be able to handle any input data length that we're providing you with. But the window size itself for your model is determined by you. If you're able to get a model that also varies window size, that would be great too. And so that part is your freedom in terms of your model's window size.
Right.
So,
So it's your choice.
for the so for the 1,000 steps, with let's say 100 known h, I can take 100 as my window size and I can start marching in terms of prediction, right?
Exactly.
Am I?
Yes.
Yeah.
Yes.
Okay. Thanks.
Yes.
Thanks.
Yeah.
But if your window need 200, then you need to tell us what do you do for the missing 100. You can
Yeah.
assume all of them as 0 or assume all of them as saturated. It's your choice.
Sorry. Can you repeat?
So if your memory, every model you need to look at the history, right? So if your model needs 200 steps of history, but we only give you 100, you will need to tell us what do you do with the other 100 that is missing that you don't know.
Okay.
Yeah.
Okay.
Any other question? Is there a way I can allow everybody to chat? I think we are almost there. I'll just ask one question. Like, if your team is still participating or have a functioning model, can you raise your hand? So that we get a sense of how many teams are still in the loop. I see 5 hands, 8, just 8. I hope there are more. There are 10 now. Okay, so maybe there are 5 teams who didn't join here. So we are probably looking for 15. That would be great. So if there are less teams, that means the chance of winning is higher. um, yeah, we are expecting maybe between 15 to 20. We hope there will be 15 to 20s holding until the end. But not being able to submit in a final participation doesn't mean a failure. I think the data is there, the models are there, and they are very interesting research. And they are the way we set up the question may not be the ultimate way of setting up the question, and you can use the data and models in whichever way you want. Okay. So are there any other question? Feedback, comments? If not, then we will conclude today's session. And this session has been recorded, and we'll put it on YouTube. Feel free to watch it and digest it. And we know we provided a lot of new information. Maybe you have more questions. Feel free to email any of us or the Pulse MagNet Gmail email address, and or leave your comments on GitHub. And we'll be happy to answer any questions you may have. And we'll try to not make any major modifications at this point, but if your comment really valuable and force us to change the rule in any aspect, we still have the option of making that change before the final data is released. So yeah, so that's all I have. I hope everyone enjoying the final miles of the challenge, holding on, and we really look forward to seeing everyone at the final stop. Okay, all right, thanks everyone. So let us know if you have any questions or comments. Thanks Shukai and Hyukjae.